name's Jordan Gums. I'm a senior software engineer at IBM. I do not play around with monitors or projectors or anything like that at all, as you can tell. And I primarily work out of the IBM Watson lab. So a lot of my day-to-day is on building various proof of concept services and demos and whatnot, centered around playing around with whatever technology seems interesting and relevant. And so a lot of time I end up finding myself in Python building services, whether they're micro or not is irrelevant. If you think whatever I say through this meeting is cool, if you want to make fun of me for what happened for the past 15 minutes, feel free to tweet me. I do have kind of a blog that I'm slowly building up. It's called tasteandtrace.co. So let's get started. So I gave a presentation at PyCon Jamaica in November about building asynchronous serverless platforms using Docker and Python. And throughout the whole presentation, I got a lot of glossy eyes. I'm sitting there thinking to myself, oh, maybe it's the serverless stuff that people were having a hard time with. And no, actually, surprisingly enough, there are a lot of people, not just at that conference, but even when I go to the meetups in San Francisco or meetups around the country, around the US, where they don't know how to use Async.io. They don't use it in their day-to-day. A lot of people are utilizing Python 2.7, or they've been embedded in Twisted or any of the other frameworks, and they don't really get exposed to it. So I like to think of this presentation as kind of like the prequel to the presentation I gave that I guess nobody here had seen, but it's okay. So let's talk about Async.io. What is Async.io? So Async.io is a Python native concurrency framework in order to build concurrent applications. I use concurrent twice because it's kind of like what it does. The idea here is that with Async.io, you have a series of tasks that you want to execute simultaneously with lots of quotation marks. We can't actually execute them simultaneously because of the limitations in the GIL, but we are able to utilize concurrent practices in order to make the most out of the one thread or the one event loop. In the case of Async.io, we have available to us. It's very readable. It's very easy to understand. There's a couple of gotchas as you go into play. And I think the last presentation kind of like hinted at, the ease of readability and the ease of development with using Async.io. So I can, let's keep going. What is it not, what it isn't? It's kind of a little bit of weird mouthful words. So it's not an automatic gift of performance. Some people that I do talk to that have used or been looking into using Async.io think, oh, I just rub some Async.io on my service or my application, and all of a sudden I'm running 10 times faster, right? No, you have to think about what it is that you're building. You have to utilize best practices. It's not just something where I can set it and forget it like one of those TV infomercial like roasters or other like Fandangle things. It isn't an answer to circumventing the GIL either. We still have to work within the confines of what Python gives us. So we know that only one real thing should be running at any given point in time. There's limitations in what it is that we can and cannot run. And Async.io is kind of a way to not so much circumvent it, but leverage the limitations we have in order to make our processes, our applications more efficient with the resource, with what it has available to it. And it isn't the end of threading or multi-processing either. As you'll see in this presentation, I actually leverage it very heavily. It's actually a very nice and clean way of utilizing threads and processes in order to, get the best out of whatever system that I'm running on. You'll notice as I go through the next slide that there are quite a few of Async.io ready packages and frameworks that exist. And I didn't even know some of the ones for IoT, because I'm not in IoT at all. But you can see there's stuff for AMQP, Bodo Core, CouchDB, DNS, Redis Locks, Zookeeper, RethinkDB, you name it. Either it's built or somebody's building it. And there's like a little link that I left over there. It's a really good wiki called Third Party that just lists a bunch of the ones that are known. Some of the stuff isn't on there, so I suggested if you know a project that's available, like, contribute to it. It's very useful for people learning how to utilize async IO. It's been picking up quite a bit of steam of late, and I use it for a lot of tasks. I tend to play around with data a lot, so I see it very valuable for doing concurrent database lookups or building out small services that take advantage of data sets that are around and available. So, but I'm focusing this talk on building microservices, and micros in parentheses because it doesn't really matter like the size or the scope of it. It could be a macro service, it could be service-oriented architectures or any large cumbersome product. But a lot of what this is focused on is utilizing the best, making the best of the resources available in order to do tasks that will have you accessing files remotely, accessing databases, doing large, heavy computational tasks. And so these are the things that whenever you're dealing with services, you're doing on a day-to-day basis. Whether it's something as simple as get the list of users from MySQL, check which user this is, make sure that they log it there, their passwords is correct, and then give them a cookie so they can go and browse your site. Or something as complex as figuring out what Docker image to instance on your swarm with the application that they've stored somewhere else, and you're aggregating all these different resources from all these different locations. It's still the same, and you're going to end up with situations, and you already do whenever you're building services, where you've got long-running tasks that could hinder the progress of other things that are running simultaneously, in quotation marks, on your machine. And when we talk about services with regards to async IO, there are two key, well, I don't want to always call it key because there are probably others that are still growing as the community's kind of wrapping itself around a few. But there are a couple main ones that at least I've been seeing, and maybe if others have been seeing other things, it'd be great to learn about them just so that I can play around with these. And it's AIO HTTP or IO HTTP, however you want to pronounce it, and SANIC. AIO HTTP is great as a one-size-fits-all kind of framework. It has the ability, it gives you the package to do client-side HTTP as well as server-side. So if you want to build a service and then you want to perform something like in requests where you want to grab something from a website, AIO HTTP is pretty great for that. And it has a lot of middleware and WebSocket implementations and all that sorts of stuff that's really great. SANIC's a little bit newer. It's not as mature yet. And it aims to be as Flask-like as possible. And it aims to be fast. Hence SANIC, he's got to go fast. So SANIC, I remember when I was at one of the meetups, one of the presenter who was a core developer at SANIC was talking about how it's way, way, way faster. And we had our morning talk about benchmarks, and he started throwing some benchmarks numbers. And I went to try it for myself. And it is really, based off of the scenario that you're developing in. But at any rate, both of these are great frameworks in order to build out services utilizing async IO. So now that I've talked about packages and things like that, I still haven't really explained in full detail what async IO is. And so I like to look at it based off of this nice and simple equation right here. So it's async plus await plus event loop equals async IO. First off, we'll look at its async. So async is just the keyword that signifies explicit indication of an asynchronous construct. It's a bunch of words. Really what it just says is it defines a coroutine or a coroutine-like construct in Python. So we look at async def. Async def indicates that you've got an asynchronous function, or what we call a coroutine. You have asynchronous async with. Async with indicates an asynchronous context manager. And async for, which indicates asynchronous iteration. these are going to be, I'll go in more in detail on each one of these as we go through. But what's also the other piece that's important is await. So await is a keyword that explicitly dictates a checkpoint within the code that you're running. I like to think of it as if you've ever played Super Mario World and you run through the level and there's that little, it almost looks like a little fence thing that you run through, and if you're a little Mario, you become Big Mario, but if you die, you start at that checkpoint again. You think about it, if you can think about it like that, it's a signal to swap to a different coroutine, and then that's the point where your current process that you've switched off from comes back, that's the point where it'll continue. So if you've got, let's say you decide that you're going to run a process, and I've got some examples. You'll run a process and you need to access a database. Well, rather than wait for the database call to finish and your process keeps running, the async IO will say, okay, I've got a long polling IO that I'm running right now. What other coroutines can I work on while I wait for that IO to complete, right? And so that's the point where it swaps off, it does whatever else it wants to do, and then you come back and you start from your checkpoint flag again and you continue on with that coroutine. It's explicit, it's easy to identify within code, and as we look at some examples, you'll be able to kind of get an idea of what's going on. And then you've got the event loop. Sorry if I'm a little loud. But the event loop is the main execution device for async IO, right? So the event loop handles registration, execution, and cancellation of all coroutines, right? And expensive synchronous calls will block the event loop until completion. Remember, we only have one thread that we can execute at any point in time because of the GIL within Python. And so the event loop is acting as that main thread that will handle tasks as it comes into the queue. So if there's a long synchronous process that hits that queue, let's say you have you're requesting that database call, even within a coroutine, if you're not doing it appropriately, you'll still block the loop, and so you won't get the benefits of utilizing a coroutine, right? In order to deal with such situations, you can just delegate expensive tasks to various executors. And again, I'll go through these little by little as we go through. Let's look at the first example. It's relatively basic. I've got a coroutine defined by async def work it. All it does is it'll sleep for a random amount of time. But during that sleep, if I have any other tasks during the sleep period, the event loop will switch over to another coroutine at any given point in time and handle any other tasks. If you look at the basic run, you get your loop, which is the event loop, and then you'll run a particular coroutine until it finishes. And so that's what that run until complete is. There's also run forever, there's ensure future, there's a bunch of other ones, and I implore you to check out documentation, and I'll be saying that throughout this. I'll give you a flavor so that you'll be able to build something quickly, but then the documentation is very great for async IO for getting more information. Are you guys able to see it? Just making sure it's clear. Okay, awesome. And because we're talking about microservices, so this is kind of like a hello Sanic, right? Hello Sanic.py. Effectively, it's got two different endpoints, and you can kind of see how it's, if you're familiar with Flask, it's got a very Flask-like implementation. You just set the route on the top as a decorator, and then you create your functions. All I'm doing is returning text, right? Sanic's great in the sense that you can have asynchronous and synchronous endpoints that handle whatever code that you want. So if you've got endpoints that all you're doing is pinging for a result, something like that doesn't need to be a coroutine. It's just going to return back like Pong or whatever. But anything that would require any form of long polling tasks, like accessing a database, accessing files, doing some form of request to another website, that you might want to think about utilizing an asynchronous endpoint and utilizing asynchronous packages in order to do that. That way, if any other tasks come in, just in case it's a long polling task, They're not blocked at all. Yeah. I think, yes, that works out. You'll kind of see I already start utilizing some packages already with event loop policy. So Sanic really likes UV loop. You don't have to do this, but Sanic claims that it's faster with the UV loop. I leave you to your own devices of playing around with it, setting your own benchmarks and figuring it out if it works right for you or not. But this will run regardless, whether you utilize UV loop to change the looping structure or not. And don't get too confused about that. All that is that Async IO has its own protocol for how it handles tasks on the queue. And there are different, other people have different implementations that they like to utilize based off of, you know, their needs and their requirements. It's something to take a look at. Obviously, documentation helps, looking at Sanic documentation and Async IO documentation. But this will run regardless. Any questions? You can feel free to ask as we go on. No. So in this case, app.run will set that loop for you. And so app.run handles the looping structure there. Good question, though. Yeah, feel free to ask. I'm trying to make sure people understand what's going on. Okay, so as I mentioned before, in a little more detail though, coroutines return a future object. And when you use await on a coroutine, it unwraps the future for the value or values if they're available, right? So if I have, in the previous example here, when I'm awaiting the async IO sleep, I don't get any values out of that. But I still have to await it because it's a coroutine that I'm explicitly stating that I want other tasks to be done while I wait for this to complete. If there is a value, it'll unwrap that in the await step, and then I can use those values as normal. What's cool though is that we can await multiple future objects. We can group them together. So if I have a bunch of different tasks that I want executed simultaneously or concurrently, I can group them utilizing asyncio.gather, and that allows me to take advantage of the event loop and coroutines and what asyncio has to offer. To note, I haven't mentioned callbacks yet. They are optional if you're more familiar with the callback style of doing a concurrent programming or synchronous programming. And I've got one or two examples, but they're optional, and you can do that using add done callback if you want to have them. Some functions will do that for you, so like run until complete or run forever will add a callback that will notify it when it's done, but that's implementation detail that as a developer you don't really have to worry about. It's only in the scenario where you've got a specific type of construct that you're building. And I've got an example that I don't want to explain now because it'll ruin it for later, but there are examples where callbacks actually work out to your advantage versus the explicit async await structure. As I had mentioned earlier about grouping grouping futures and grouping coroutines. So this example is very similar to the example that I had in the previous, where all I'm doing is waiting a certain number of seconds until it complete. But here, now I've got a bunch of ones. I set up a bunch of futures utilizing a list comprehension. So I want to 5 different futures, up to 5 different coroutines that I want, running concurrently. And then I group them using asyncio.gather. And you see there's like star futures. So I have to I'm unpacking the value of the list that I've generated. And then I will wait on that group future object, which will unpack the list of future objects that I have gathered as they complete, right? So if I want to run 10 of these at once, I can run 10 of them without awaiting them. I can group them up into one, and then I can await them at a later point in time. So this is useful if you want to make sure that you got all of them running, and then you've got other small tasks that you want to fulfill before getting the results. Any questions? Is it clear? Not clear? Okay, cool, cool. So here in Sanic space, I've got another example here called outbound Pi. So in this example, all I'm doing, it's nothing too special, but all I'm doing is showing how I can write a coroutine endpoint that can grab information from a remote site, so at this point, ibm.com, and then return to me a simple JSON object, right? So as that's being done, I can hit this 10 different times, and each one of them will complete, as they complete, regardless of the order, they'll send me back the information that I need, right? Executors. So executors help us utilize synchronous functions asynchronously. So I had mentioned before that there's a bunch of different libraries available, but those libraries are kind of a small subset compared to all the libraries that are available to us in Python land. And sometimes we still want to use them while building asynchronous applications, asynchronous services. And so we can utilize executors in order to do this. And so we take our event loop, so loop.run an executor, and then we provide or don't provide an executor, and then the function and its arguments. And that will run whatever it is that we need to run asynchronously utilizing an executor. And what is this executor? So an executor is either a thread pool executor or a process pool executor. Notice now we're using threads in order to handle synchronous functions asynchronously. And the threads and the processes never actually went away. Actually, we can use it to our advantage. So rather than building out a thread pool executor and then maintaining locks and doing a whole bunch of other things, I can split up the processes or the functions that I want to run in a way such that they can be isolated, and then utilizing this structure, I can run them. They run off on their own, assuming that it's IO bound function. You use a thread pool executor. If it's CPU bound, you use a process pool executor, and then I can still run my asynchronous tasks through the event loop until those complete. And this is primarily because for these types of functions, if it's IO bound, then the GIL will normally, for function packages, the GIL should release for those type at the point where it's waiting for the IO. And for CPU bound, it's split off into another process, and so that process is running, and when it completes, it just shunts the data back into the future object that the executor, run an executor provides us. Note that if you're using any functions that require keyword arguments, you will have to use functools partial, which means that you have to create your own partial function in order to pass that along, because the executors don't like keyword arguments for some reason. Yeah, and I suggest, for the most part, in all the examples that I have here, I don't build my own thread pool executor. And this is because if you set executor to null, it defaults to a thread pool executor. So it's relatively simple to build out these things for synchronous functions in asynchronous applications. So here's an example. All I've got here is I'm trying to access the IBM website, and I want to get the status code and the body length, right? But in this case, I'm not using an asynchronous framework. I'm using requests. Requests is synchronous, right? So what's going to end up happening here is no matter how many times or how many instances of these that I run, I'm going to be blocking my event loop whenever I try to call result equals request.get, because I have to wait for the IO to retrieve the web page object and bring it back so that I can run my other the calls afterwards, right? But now, if I really want to use requests, I can wrap requests in a executor, thread pool executor, using loop.runInExecutor. I set executor to null because all I'm doing is running a simple request. I don't care about how many different threads or all the stuff that concurrent.futures thread pool executor gives me. And I just pass in the parameter www.ibm.com, and then I wait until the I/O is completed before I continue on. So if I've got other things that I'm running, if I'm hitting databases, hitting other websites, it'll do that just fine. And see here, I've isolated in case you can't see it. Right. Cool. And so I had already shown you AIO HTTP in one of the Sync examples. This is me just doing the same exact thing using the AIO HTTP.requests. Right? I don't have to worry about executors because it's an asynchronous framework. Okay, so I can quickly, let's show some code. Hopefully it will be visible. That's too big, or yeah, it's too big. Can you see that? Is that visible? Okay, cool. So here I've got some simple, well, it's quite a bit of code. Let's see. I'll go to the client here. Here we go. So this is just an example from one of the projects that I've been working on. It's about building your own synchronous platform. And so when I was building this platform, for the most part, I didn't have an asynchronous Python Docker framework to work with at the time. I know AIO Docker now exists. It's slowly gaining traction, slowly gaining more committers. I hope to commit something at some point. But one of the issues is that I've got to interact with containers all the time. And when you're interacting with containers, you have to establish a connection to to Docker, and then wait for Docker to establish a connection to the actual container itself. And then you've got to pass data depending on depending on what type of function you're working. So in the project that I was working on, it was either a simple HTTP request where you send off one payload and then it gets ingested by Docker to be embedded into a Docker image container at runtime to handle to use parameters to run its task to send back information. I hope that's not too confusing. It's just a lot of data being sent all over the place. Or in the case where it's a WebSocket, I actually have to connect to the Docker Unix socket, the actual containers Unix socket, and then pass data through that socket and then stream data back to the user, right? And so in both these cases, it's a lot of I/O that's happening, and I don't have async Docker. So a lot of what I end up relying on is using executors. So in this example here, I'm trying to spawn an action. So when I spawn an action, if you've done anything with serverless before, serverless, you have these serverless functions, and then these functions get stored somewhere to be retrieved at whenever you need to run a function. You hit like an HTTP endpoint. In this case, a lot of the times this is done using containers. So they inject the function into the container, runtime, and then run it, and then you get the results and send it back. So this is very similar to what's going on here. So I have to create a container, and when you create a container, there's a lot of keyword arguments. So I have to utilize functool partial in order to create a partial function here. That way I can get standard in is open, detach an environment if you're familiar with Docker at all. And then once I get my partial, then I can send that partial function into an executor to create my container. And then once the future is created, I can then await on that future. And then at that point, I can then just start my container, right? And so now I start the function and it's running, and then I can have a subsequent call where I can retrieve that information back and send it back to the end user. If you're interested in this at all, I have it. I have it on my GitHub account. It's called Amethyst. I think I like it, but you know, maybe other people. It might be something interesting to look at to get some kind of ideas. That's all written in AIO HTTP. It was before I found Sanic. But some of the key points is like utilizing Executor and functools partial in order to handle those types of functions. Yes? Okay. So that is an implementation. So in IBM land, we call serverless functions actions, and so an actor is something that performs the action. So in this case, Docker is the actor for this example, and so Docker is spawning off these actions for us to retrieve the information. No. Thanks. Good question. Okay. So we've talked about async, we've talked about await, we've talked about coroutines. Let's talk about context managers. So if you're familiar with context managers, hopefully everybody is, whenever you open a file with open blah, 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 as blah, 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 that's a context manager, right? That's utilizing context manager. So in async land, it's very similar. So in regular context managers utilize enter and exit. You have to implement these two pieces in order to have a context manager. It's not a context manager without it. In this case for async, you just have to implement a enter and a exit. Asynchronous enter, asynchronous exit. And these can wait on I/O or CPU depending on if you've got a thread pool or if you got a process pool executor, a thread pool executor, or if it's just a simple asynchronous package. It can wait on that while creating and destroying these sessions that we create, right? So I have an example session here called player state. So let's say I've got a game that I'm making and I want to make sure that only one game or one person is tampering with a state at any given point in time, right? So maybe I want to create a context manager that can, when I try to grab a certain player state, it locks that state down for me and then grabs the state information from the state database before allowing me to do any manipulations. And then when I exit, I want it to push the final state of that state, and then release the lock so that somebody else can manage or manipulate that state of my player state. So here, all I've done is, and I hope it's easy to see, all I have here in the a enter is, when you hit the asynchronous enter, I grab some lock, and then once I grab the lock, then I try to get some state. And in this case, getting state is some synchronous function that probably hits utilizing a synchronous database package or something else, some other thing, and giving the player ID in order to grab that state. And then once I have the state, that I can manage, manipulate, do whatever. And then on exit, I just check to make sure that the state has a lock attribute and a state attribute. And if it does, I push state and then I unlock, right? And then when I look at it from using, all it is async with player state, player as PS for player state, and then I do a simple foobar update, and then I print out the state, and voila, it's relatively easy to utilize. Very similar to using regular context manager. And then we have async for. So this is for iterate and generate. So all it is a looping construct for handling iterators and generators. And if you want an iterator, iterators must implement a iter and a next. Very similar to if you're writing a standard iterator, you have to implement iter and next, right? So here I've got another simple example, next suites. I've got that same game again, and now I want to be able to randomly generate the next little candy or treat icon that falls into my stage as I play, right? So I've got my list of sprites, and this is the iterator example. I've got my list of sprites, bonbon, taffy, mochi, cookie, and cake, and I initialize it, so I set where I'm starting and to where I'm ending, and that's something that I retrieve whenever I try to gain new states. And then a next is the primary one that we care about, because a-iter, all you want to do is return the iterator, so then you can continue to use that iterator. But in a next, I have a stop iteration state, so at what point do I want to stop the iteration? If I don't, and I want it to go forever, I don't need to worry about it. But other than that, all I'm doing is incrementing the current position of where I am within this iteration, and then I just randomly grab a suite from the list of suites that I have up there. I have a sleep there just to like mimic if I'm hitting a database call. Maybe I want to make sure nobody's cheating, so every new suite object I create has an associated ID that's associated with, so if I ever want to replay the game and check to make sure that these are actual legit candy items that they're grabbing, then I can do that if I want. I don't have to. And then I just return whatever is the next thing that I wanted to return. And then implementing and actually using, all I do is I've got async for suite and next suites of k, and then print suite. Very simple, very similar to using regular iterators. All these examples, I have a GitHub if you're interested in like grabbing them and like playing around with them. So I'll try to release that link later in case you're interested. Same thing with async for, but now we're looking at generators. I personally like generators because they're a lot easier to deal with. I don't have to build a class object for every type of iterator that I want. I can just build this generator out. And all it is I have async def next k suites, and then for I in range of k, I simulate a blocking call by using a sleep. That could be a database, that could be a service, whatever. And then I just randomly generate the next suite and then yield it out. And just like that, I've got my generator. And it's utilized in the exact same way. And so, example. So another project that I've been okay, there it is. Another project that I've been working on has been primarily utilized in Async, is one where, let's do this. I've got a bunch of StarCraft 2 data. And what I'm trying to do is I want to be able to do analysis on it. I want to be able to store that data somewhere in some set of databases and then pull it back whenever I want to download it to do any more detailed analysis. Because we get, in our lab, we get about 500 StarCraft. We've got like a esports project. We get like a bunch of new StarCraft replays from players who we ask, and they send it to us whenever they feel like it, and then we've got to ingest it. So an example here in Async. So this is showing how I can utilize asynchronous generators in order to stream back data to the user. So if I want to download a state, like a replay that I have in this case, I've got it in IBM object storage, but it could easily be S3. It could be a file on somebody else's computer, what have you. And all it is I'm grabbing the data and the byte size. I'm just asynchronously iterating through an object storage connector object that I've stored within my app that allows me to access either upload, download, or edit any objects in my object storage. And all it is I grab it, and then I write it out to a response object, and I send it out. And so one thing to note is that right here, I don't know if you can see it, sanic.response.stream and stream. So this is one of the few examples where I actually do like having a callback. So this is Sanic implements streaming back to the user through callback. So you create a callback function. In this case, it's asynchronous coroutine stream that will just iterate through every single time I grab more bytes from a chunk of an object that I've got stored somewhere remotely. And all I'm doing is grabbing that chunk and relaying that chunk back. I'm not storing any of the data locally on my, in memory. I just grab it, write it out, grab it, write it out as it comes in, as opposed to grabbing the entire object and then re-chunking it back out to the user. I don't know how large this file is. I don't want to know. I don't want the machine to know. I don't want to feel how large that object is on when I'm running my processes. Because if it's eating up memory, then I have to worry about performance issues, right? And so this is implemented in Swift. If I can find it. Here. So right here, this is where I have both some asynchronous context managers, and I've got an asynchronous generator at the same time. So I'm creating a session object utilizing AOHTTP that will handle all of my requests to the Bluemix object storage. In this case, it's implemented as OpenStack Swift, but I mean, that doesn't really matter all that much. But it has specific protocols to how you get large objects. And so it has setup for how you chunk it, et cetera, et cetera. And so this, all it does is I get the next chunk of the object, I send it back through the generator, and then I wait until I get my turn again to then grab the next chunk over and over again. I don't try to hold on to any of the objects, I just grab it, send it out, so on and so forth. And it's really good. It's one way of utilizing generators whenever you're trying to retrieve objects, but this is one way of doing it. There are plenty other ways to go about it. You can create an iterator object if you'd like. I don't know if it's readable. Is it easy to read? Good? Okay, awesome. But yeah, and so in this case, like I've got an end state where if there's no chunk of data, then I just yield none, and then that's the end of my iteration. Right. Go back here. Cool. So, again, don't feel the need to think that async IO has to go everywhere. I mean, I like using it a lot, and I end up using it a lot, but it's because I build applications to where I'm constantly having to worry about, making the best out of my resources for services that I'm building. I could easily try to build this using thread pool executors and things like that, but async IO actually gives you a nice framework for utilizing threads, just not in the thread pool way. You're still doing it in the asynchronous way. So you're still waiting on things. You still have to think about how you break apart your tasks in order to make the most efficient usage of threads, of processes, of asynchronous packet frameworks. So again, not everything has to be a coroutine, right? Try to use async IO packages when they're available if you need to use async IO, right? And then use executors if they aren't available, and if you need to use async IO. Well, unless you have to use thread pool executor or process pool executor, then do your thing. I won't stop you. And that's pretty much everything I have. Are there any questions? No? Well, thank you very much.